Hello everyone. Today we'll be presenting our project titled Short-Term Solar and Wind Power Forecasting using Machine Learning Models for Microgrid Operation. This project is part of our Engi 990A MESE project, and our coordinator for this project is Professor Mohsin Jamil. I am Omar Kyoda Emmanuel, and alongside my teammate Vidi Patel, we aim to explore how machine learning can be harnessed to enhance the efficiency and sustainability of microgrids. Throughout this presentation, we'll walk you through our research process, our findings, and their potential implications for future renewable energy planning and smart grid systems. Here's a quick outline of what we'll cover today. We'll begin with the motivation behind this project and the global push toward clean energy. After that, we'll explain our objectives and the importance of short-term forecasting. Then we will discuss the dataset and our methodology, highlighting how we applied random forest and LSTM models. We'll walk through our results, compare them with literature benchmarks, and then wrap up with key takeaways and suggestions for future work. We'll conclude this with time for your questions and discussions. The world is rapidly transitioning to renewable energy, yet integrating sources like solar and wind remains a technical challenge. Their unpredictable nature makes it difficult to ensure reliable power, especially for isolated or off-grid communities. Without accurate forecasting, microgrids often rely heavily on diesel generators, increasing fuel costs and emissions. This project addresses that challenge by applying machine learning for short-term predictions. Our aim is to make microgrids operations cleaner, cheaper, and more stable by forecasting fluctuations ahead of time.
Our main objective is to create a forecasting framework that can predict solar and wind energy production hourly using machine learning. This involves using historical weather data and power output to train model capable of anticipating trends. We choose random forest and LSTM models due to their unique strengths in handling structured and sequential data respectively. By doing so, we aim to enhance load balancing, optimize energy storage usage, and reduce reliance on non-renewable backup sources like diesel. Ultimately, this project supports smarter and greener energy planning. Dataset. The dataset we used comes from a well-known forecasting competition held in Portugal and includes 4 years of high-resolution data. It captures photovoltaic power output and meteorological variables such as wind speed, temperature, and humidity. With 5-minute sampling intervals, the data is rich and detailed, offering an ideal foundation for training machine learning models. It also includes power demand and generation data from local wind farms, which allowed us to explore both supply side and demand side dynamic in our model process. Let's move to the methodology. So our workflow started with data collection and pre-processing. This involved cleaning missing values, normalizing ranges, and engineering relevant features like hour of day or solar zenith angle. We then split the data into training and testing sets, typically using an 80-20 split to evaluate generalizability. Next, we train random forest and LSTM models on the same dataset to enable fair comparison. To access accuracy, we use metrics like RMSE, MAE, and MAP. These statistical tools help us determine which model was more reliable and by how much. So, the first method we used for our project is random forest. Random forest is a popular assemble method that builds multiple decision trees using subsets of data and features. Each tree gives a prediction, and the final result is an average of all trees. This approach helps reduce variance and overfitting, which are common in single tree models. We also leveraged the out of bag error to internally validate the model without a separate validation set, while random forest handles nonlinearity and feature interactions as well. It its main limitation in our case was its inability to recognize time dependent trends, a crucial factor in renewable forecasting.
Long short-term memory networks, or otherwise called LSTMs, are a special kind of recurrent neural network well suited for sequential data. They use memory cells and gates to retain important information over time, which makes them effective for tasks like weather and power prediction. We configured our LSTM to receive sequences of 56 hourly data and predict the next hour's power output. The model was trained over 50 epochs. LSTM's advantage lies in its ability to model cyclical behavior and capture long-term dependencies, which are very important in solar and wind patterns. To discuss the performance of the LSTM model, we generated a graph which is shown here on the right. The graph shows how the LSTM model performed over 1 week period. The blue line shows actual power generation, and the orange line shows the predicted power generation by our LSTM model. As you will see in the graph, the lines almost overlap entirely, particularly during solar cycles, daily solar cycles. This demonstrates the model's capacity to learn the generation rhythm. Even during rapid environmental changes, such as sudden cloud cover, the model maintained a respectable accuracy. Our average MAE was about 97.52 kilowatts, which is well within acceptable forecasting limits for microgrid planning and usage. Okay, looking at the performance of the random forest model, unlike the LSTM, the random forest often overestimated power output, especially at night when there should be zero solar generation. We can see from the graph that the overlap is not as profound as it was with the LSTM, and we can see some visible misprediction by the random forest model. This issue likely stems from the model's lack of time awareness. The RMSE and MAE values were significantly higher, indicating poor prediction quality for low generation periods. We also tested RF during our non-solar hours and still predicted large values, revealing its limitation in distinguishing night from day without explicit time-based features and explicit instructions.
Benchmarking with literature. To validate our approach, we compared our results with published findings from other research papers. We plotted our LSTM and random forest outputs alongside results from two other studies. As shown, our LSTM performed comparably and in some cases better than existing models, especially in matching peak outputs and maintaining smoothness. Benchmarking like this is important. Here you can see the graph that we compared our results with the actual data and other benchmark. Our result is nearly similar with the actual data, and other benchmark is probably inaccurate with the actual power. And it shows that our method isn't just accurate on our dataset, but also holds up when compared with established techniques in academic research. In summary, our project illustrates that machine learning, especially LSTM, can play a key role in renewable energy forecasting for microgrids. Accurate forecast enables smarter load scheduling, reduced fuel usage, and enhanced grid reliability. While random forest offers simplicity and speed, LSTM's strength lies in modeling complex, time-based relationships. This makes it better suited for energy system influenced by weather patterns. These insights can inform energy policy, guide real-time operations, and support remote communities in achieving energy independence. Going forward to the future work, that we see several opportunities to improve this work. First, we can refine the random forest model by including time-aware features like sine, cosine hour encodings. Secondly, we aim to incorporate diesel generator dispatch logic into the forecasting framework. Third, we want to test other models such as GRUs and hybrid LSTM CNN models. And finally, we envision developing a real-time dashboard to visualize and control forecasting for microgrids, potentially integrated with actual community-based energy project. If you have any question or suggestion, we are open to feedback and discussion. Thank you all for your attention.